Hello and welcome to GCSE Chemical Changes with Mrs Castanera. We're on lesson 13, Electrolysis of copper. Our keywords for this lesson are ion, electrode, anode, cathode, electrolyte, molten, solution and redox. Many of these words we've come across before. So we're going to start by doing the knowledge check. There are 8 questions. Pause the video whilst you complete these questions, please. Okay, so let's go through those. I'm afraid the answers are not written in red today because my red pen has run out. So, state the chemical formula for copper. It's Cu, capital C, lowercase u. State where the electrons are found in electrolysis. Well, they're found in the current, or you could say in the wires in electrolyte. Suggest why a carbon anode requires continuous replacement. That's because it reacts with the oxygen, forming carbon dioxide. Just saying it reacts with the oxygen is sufficient for the mark. Name the gas formed when oxygen reacts with carbon electrodes. Well, that would be carbon dioxide or CO2 for the mark. Define inert, that means unreactive. What does AQ represent? Well, it represents aqueous or dissolved in water, either of those for the mark. Explain why carbon can displace copper from copper oxide. Well, that's because carbon is more reactive than copper. And name the 2 nonmetals in the reactivity series. Well, they are carbon and hydrogen. You need both for 1 mark. So that's a total of out of 8, please. Give yourself a mark out of 8. So by the end of today's lesson, you should be able to explain in terms of reactivity series why some metals are extracted with carbon and others with electrolysis. You should also be able to predict the products of electrolysis of aqueous solutions containing a single ionic compound. It's the same as last lesson. We're going to develop this further. So, reduction or electrolysis, that is the question. Okay, so metals can be extracted from molten compounds using electrolysis. We know this. Electrolysis is used if the metal is too reactive to be extracted by reduction with carbon, or if it's reactive with carbon. We can extract copper from copper oxide by performing a displacement reaction. The copper is displaced by carbon, okay, to form carbon dioxide and copper. This process requires large amounts of energy and it can produce a lot of carbon dioxide, and this contributes towards global warming. So this is very bad for the environment and it's also very expensive. We're going to make a note about that. Okay, so carbon dioxide is bad for the environment. It contributes towards global warming and climate change. Also, the large amounts of energy you require to do this makes it expensive, as well as being bad for the environment, because the large amounts of energy typically come from coal or gas-fired power stations, which are also producing carbon dioxide and other greenhouse gases, which are, again, bad for the environment. So, moving on, in electrolysis, large amounts of energy are used in the extraction process to melt the compounds and then to produce the electrical current. So again, it's expensive and bad for the environment. However, it's not producing quite as much CO2. So once copper has been extracted from copper oxide by reduction, it needs to be purified, and that's really important. So for copper, it's not so much a choice of reduction or electrolysis. In fact, you have to use both. So the copper that you've extracted through reduction is now unsuitable for use in wires in electrical circuits. So you have to then go ahead and electrolyse or do electrolysis on that copper you have just spent all that energy and produced all that carbon dioxide for. So then we use electrolysis to purify it, and we're going to use an electrode made from the extraction and an inert electrode of carbon. And this will purify the copper if you're using the correct electrolyte. And we won't worry about what that electrolyte is. Just suffice to say, it doesn't always happen unless you use the correct electrolyte. So we're going to add a note about copper requiring both forms of extraction here. Okay, so if necessary, you can pause the video to make sure you've written this all down. So this says that to extract copper for electrical wires, we must use reduction and then electrolysis. This means that electrical grade copper is very expensive to produce and very bad for the environment. So you can see how actually some metals become extremely expensive. So copper is not hugely rare, it's relatively common, but it's very expensive to extract it. and that's what makes it expensive to buy. There are metals that are expensive, such as gold and silver, not because they're difficult to extract, but in fact because those are unreactive, but they are expensive because they are very rare. Now, sometimes along comes a metal in our periodic table that is both very rare, like gold and silver, and very expensive to extract, like copper. And those are the super expensive materials that cost a lot of money to produce, and they are very bad for the environment, and they are very, very expensive. Typically, these metals and these materials are used in things like mobile phones and other electronics, devices that typically are very expensive, and they're often used in very tiny amounts, again, often in electrical circuits. So, moving on to page 36, we're now going to look at purifying copper using electrolysis. Now, unfortunately, this is a practical task that we can't do, but we're going to talk about it and we're going to have a go at this diagram. So, your task is to label the diagram with the following words: electrolyte, that's copper 2 sulfate, the copper anode, the carbon cathode, and DC or direct current. You're going to draw the ions of copper, that's Cu2+, and the sulfate ions, that's SO42-, and you're going to draw those next to their appropriate electrodes. That's very important. Then you're going to draw the products at the anodes and cathodes. Then you need to show the movement of the electrons in the electrodes and the wires. So some simple arrows to show direction will be suitable. So don't forget you need to do that in the electrodes, so that's the cathode and anode, and in the wires. Okay, so pause the video whilst you have a go at this question, please. Okay, so let's go through that. Now, this is quite a complex concept to cover, so don't worry if it doesn't make sense to you straight away, okay? But we will work through it and you can watch it again if necessary. So first of all, label the diagram using the following words, and I've already missed a mark because I did not label my electrolyte, which is copper 2 sulfate. Okay, so you get a mark for labelling your electrolyte, copper 2 sulfate, the copper anode and the carbon cathode, as well as the DC direct current supply. Next, it asks you to draw the copper ions next and the sulfate ions next to their appropriate electrodes. So sulfate here is a negative ion attracted to the positive anode, and I've done 2 of them. And then the copper ion here and here next to its positive charge next to the negative anode. So mark out of 4 for the first one. Okay, mark out of 2 for this second one, 1 for each. Draw the products at the anode and the cathode. Okay, so the products at the cathode is copper. So you could put Cu here like this, or you could write buildup of copper on the surface of the cathode. Anything to indicate that copper is building up at the cathode. Now, the anode, the product is essentially Cu2+, copper ions from copper, because this anode is dissolving. So you could do that through this diagrammatical method here, or you could write it here to say that the copper anode dissolves, either via oxidation, loss of electrons. Okay, so mark out of 2 for getting each of those. Question 4, show the movement of electrons in the electrodes and the wires. So any arrows such as this or this to show the direction. Here I've done individual ones. This shows 2 electrons leaving my copper in the anode and going towards the circuit. So if you've done that, you can have a mark. Also, you might have done 2 electrons here coming from the cathode into the Cu2+ ions. So you can have a mark if you've done that too. So the half equations for this, so here we have Cu, take away 2 electrons, gives us Cu2+, this is oxidation, which is loss of electrons. You don't need to do this to get any marks, this is more just I want you to add this. And then here we have reduction, gain of electrons of the copper 2+ ions, add to them 2 electrons to turn them into copper. And this is how electroplating is done. So first of all, I want you to pause the video and make sure you've got all of this information written down, please. Okay, so moving on. So as I've said, this is how electroplating is done. Now, electroplating is covering a material with metal, okay, using electrolysis. And I will add that part. Okay, so make sure you've got all that information written down, please. Okay, so now we have the half equations at the electrodes. So firstly we have the cathode, where Cu2 plus added to that is getting 2 electrons to turn it into just pure copper, and that's being deposited on the surface. Now, if your anode is made from carbon, okay, then you will get carbon was produced, oxygen gas being produced. Now, our anode is not made of carbon, our anode is made from copper. So what we had was our copper anode produces, well actually it's dissolved, okay, so this is the half equation for the dissolving of the copper anode, which is what happens when you have like an anode made of copper. If your anode is made of carbon, this happens instead. So water dissociates and turns into 2 oxygens, which are gassed off, 4 hydrogen ions, which are positively charged, and 4 electrons. Okay, that means that it produces oxygen gas. Okay, there is another way to write this, and I'll show you that. Okay, so there is the alternative method of writing this. So water, take away 4 electrons, turns into 2 lots of diatomic oxygen. So that's 2 lots of water, turns into 2 lots of diatomic oxygen and 4 lots of hydrogen ions. Okay, so make sure you've got all that written out and that you're clear that a carbon anode will produce oxygen gas and a copper anode will be dissolved and then deposited on the on the cathode. Either way, the cathode will have copper deposited on it. So moving on to the checkpoint question on page 37, aluminium is manufactured by electrolysis. We know this. Part A asks you to suggest why reduction with carbon is not an appropriate method to manufacture aluminium, for 1 mark. Part B asks you, in the electrolysis of aluminium, what is the cathode made of? Then part C says, in a mixture of aluminium oxide and cryolite, that's what forms the electrolyte, explain the purpose of the cryolite. Keyword in here is explain, and that is for 3 marks, which means you'll have to say more than one thing. You'll have to say 3 separate things. So think about things you could say there. Part D says to, again, explain why aluminium is produced at the cathode, and that is for 2 marks. So keyword here is explain. So pause the video whilst you complete those. It might take you a while, and then we'll go through it together. Okay, so let's go through that. Question A, suggest why reduction with carbon is not an appropriate method to manufacture aluminium. Well, there's 2 options here. You can say that aluminium is too reactive to be extracted by reduction, or you could say that it is more reactive than carbon. Either of those can get you the mark, maximum of 1 mark for this. Then for B, in the electrolysis of aluminium, what is the cathode made of? You can say carbon or you can say graphite. Again, 1 mark. So marks out of 1 for A and mark out of 1 for B. Part C, so a mixture of aluminium oxide and cryolite forms the electrolyte. Explain the purpose of the cryolite for 3 marks. So, first of all, you have to say that aluminium oxide should be molten. It has to be molten for electrolysis to occur. So you have to talk about the fact it's got to be melted or heated up. Then you can say that cryolite lowers the melting point. So this statement here for a 2nd mark. Then you can say that less energy is required, and that makes it cheaper. So there's 4 ways to earn a mark there. It's out of 3, so it's up to a maximum of 3 marks there. Moving on to part D. So part D says, explain why aluminium is produced at the cathode for 2 marks. That's because aluminium ions have a positive charge. You talk about those aluminium ions having a positive charge, or you can write Al3 plus to show that it has a positively charge. And then you should say that they are attracted to the negative charged cathode. Okay, so they're attracted towards that negative charged cathode. You don't have to say cathode, as long as you say it's attracted to the negative charge, then you've implied it's at the cathode. And that's out of 2, please. So give yourself a mark out of 7 for that whole thing. Okay, make sure that you've written out everything that you got incorrect or didn't get fully correct. Make sure it's 100% right before you move on, please. So that might be too big, but you can always rewind the video to find the correct place if you can't see all that text. So we're moving on now to the knowledge check on page 38. Please answer the questions, pause the video whilst you do that. Okay, so let's go through that. State the reaction used to reduce copper oxide, that would be carbon. Explain why the reduction of copper oxide is expensive. That's because it uses a lot of energy. Question 3, state what AQ represents, or aqueous, which means dissolved in water, so you can say that for a mark instead. Question 4, give the products from the reduction of copper oxide, so that's copper and carbon dioxide, you need both for the mark. Question 5, state the material used for the inert electrodes, that would be carbon or graphite, either of those is acceptable for the answer. Question 6, name the electrolyte used in this process, so that would be copper sulfate. Question 7, state where the reduction is happening in this process. Reduction is happening at the cathode, the negatively charged electrode. And question 8, give the symbol for an electron, that's a lowercase e, negative charge, so that's a superscript. Give yourself a mark out of 8, please. And we're going to move on now to the application knowledge on page 38 as well. Okay, so there are 3 questions. Question 1, explain why copper builds up around the carbon electrode. So that's an explain question. Question 2, again, it's an explain where the oxygen around the anode comes from. And question 3, explain why we use inert electrodes. Now, before you do this question, I just want to add something to this. So I want to highlight for question 2 that you only get oxygen forming around the anode if your anode is made from carbon. You do not get this oxygen if your anode is made of copper. So explain where the oxygen around the carbon anode comes from. Okay. So pause the video whilst you answer these questions, please. Okay, so let's go through those. Question 1, explain why the copper builds up around the carbon electrode. So, firstly, the negative cathode, which is the carbon electrode, donates electrons. So it donates electrons to the positive copper ions, which then turn into copper atoms, and that builds up on the surface. Okay, another way of writing this is say the negative cathode donates the electrons for the first mark, so I should be marking in green here. So talk about donating electrons, then positive copper ions turn into copper atoms, or positive copper ions donating electrons turns into atoms. So this equation here would cover all 3 marks, okay, as long as you explained that the electrons are donated from the negative cathode, okay. So that's a mark out of 3, please. Question 2. Explain where the oxygen around the anode comes from. Well, water dissociates into H plus and OH minus ions. You have a mark if you've said that, or if you've shown it here like this. Okay, now OH ions travel to the anode because they're attracted. In fact, I should probably add that. They are attracted because they're oppositely charged. Okay, not just because they can move, but because they're attracted by the charge. So they are going to travel to the anode because they're attracted, that's a mark. And then they're going to lose electrons, which is another mark, and form oxygen for a 4th mark. Okay, another way of writing this is 4H minus, take away 4E, 4 electrons. It turns into O2 and 2H2O. So if you've done that, that's worth 2 marks there, okay? And all you would need to do is have, if you've written both those equations, all you would need to then say is that the OH minus ions are attracted to the positively charged anode. So that's a mark out of 4 there, please. Okay, so question 3, explain why we use inert electrodes. Well, the idea is that the products of electrolysis don't react with the electrodes. If you say so that it doesn't react, that's a mark. and it's out of 1, this one. As an interesting aside, I do want you to write this down. So the oxygen that's formed here in this example actually typically reacts with the carbon anode to make carbon dioxide instead, as shown by this equation here. So you don't actually get oxygen. This is not a sensible or useful way of producing oxygen because you generally get carbon dioxide and oxygen mixed together. So there's another question on the next page. If you haven't noticed, pause the video again whilst you do that. If not, we're going to go through that now. So question 4, suggest what happens to the sulfate ions, SO42-, during the electrolysis process. Well, they are attracted to the positive anode because they're negatively charged. You have a mark for that. But actually, the reality is that nothing happens to them. If you said nothing happens to them, that's because they're too stable, or you might say that other ions are affected instead. Okay, so give me a mark out of 2 for this one, please. Okay, so this whole thing is out of 10, so give yourself a mark out of 10 for the whole thing so far. Now I'm going to move on to the extension activity. Okay, this is something you're going to do in your own time. If you want to check your answer, feel free to email your teacher or ask your teacher in person. So in 2007, the price of copper was £3,000 per tonne, and in 2010, the price soared to £6,000 per tonne. Suggest why the price of copper increased so dramatically over the 3-year period. So as this is something you're doing in your own time, that's the end of our lesson and the end of the topic as well. So well done, and thank you very much.